Yeah, thank you. I'm providing a terrible example of not having good microphone discipline. But yeah, so we are webcast, and so please always use the microphone. But I would like to start off, I want to introduce Joe Stetter is our keynote speaker for today. He has worked in developing sensors for years as a true expert, particularly in the area of how do you move newly developed very innovative and new technology into production. And since we are running a little late, I'm going to toss it straight to you without much introduction, since the important part is what you have to say, not how I introduce you. So thank you very much.
Okay.
Are you ready to go?
Do you have a timekeeper? I don't need this. Okay. How much time do we have?
You have 45 minutes to talk. Maybe to do about 5 minutes for questions. Because we'll have
Okay, thank you very much for inviting me here. I want to say that science uses facts and knowledge, and we try to build things. And my colleagues at the university, I was in the chemistry department, always criticized me for being too much of an engineer, and the engineering faculty always criticized me for being too much of a scientist. So I was fortunate to have a career that I could do a lot of what I wanted to do. I have to apologize to everyone. This is not a comprehensive talk in any way, shape, or form. It's not a faculty lecture of how to do things, but it's a compilation of my experiences. And I hope that by these we can get some insights together into how to transition things from knowledge and ideas into products for people. And in the meanwhile, what role manufacturing plays. And I have to tell you that over the 40 years that I've been doing chemical sensors and gas sensor research, I've managed every year to be at the limit of my knowledge and need to learn new things. So I think that's just the way it is when you're doing things. Okay, so this is two companies, KWJ Engineering, which I did a leverage buyout in 2007, and then SPEC Sensors, which a group of investors spun out some of the technology to make sensors. That's the relationship between these companies. And let's see. It works. So KWJ, just tell you just briefly, really briefly, what we're doing is KWJ, our vision is to improve human health and safety, security, and our environment by providing next-generation detection products, analytical chemistry in a box or cheaply. And so we've got a bunch of people with all different kinds of degrees, mechanical engineers, chemical engineers, physicist, electrochemist, analytical chemist, I said mechanical and electrical engineering. But all of these guys have one thing in common. They're focused on building sensors into useful devices. So I put these slides are a compilation of things. Some of you might have seen these over the years. But to do a sensor, you have to do some design work, then you have to build it, and then you have to test it. And then based on what you learn and evaluate, you go back and you redo the design, you fabricate, and you retest. And you iterate until you get the specifications that you need to solve a problem. And that's unbelievably simple, but that's what you do. So right now, our company is making a line of products under the EcoSensor brand, which are small portable ozone instruments that, for example, in casinos, they clean the air from cigarette smoke with ozone in the plenum, and then they have to dump it back into the casino, and they have a little box on the side that assures that it's not more than 50 parts per billion. And we make that kind of machine. It's used in laundries, it's used in the Monterey Bay Aquarium, lots of different places. We make an inline OEM carbon monoxide alarm for breathing air, for medical breathing air. And we make a portable, wearable pocket CO for carbon monoxide protection. Basically a home CO alarm in your pocket. It's a little better, it does health levels. And then we're starting to do wireless and IoT applications. SPEC Sensors is only sensors, and we've taken the current industrial design and shrunk it down, and there's two big innovations here. One is to reduce the size and the materials and the cost, but also to get a paradigm that the process you use is like silicon wafers. You build it up on wafers with additive and subtractive screen printing types of operations, and so then you're able to build it not only high performance but also low cost, and that's turning out to launch SPEC sensors. And we passed UL 2034, which is the home CO regulation, and the European one just this last year. And so the quality of this, even though you shrink the size and the cost by orders of magnitude, the quality is still very high. And we're going to come out with a even smaller one. When you get one, that's interesting. We had one that's 15 by 15 by 3 millimeters, and then they wanted 10 by 10 to do wearables. We had a request from a customer. Now customers are saying, well, what about 3 by 3 millimeters? And you know that you can never retire. It's not possible. So we have a bunch of intellectual property, and many of these things you'll see in a lot of nanosensors, of course, small size and high activity nanocatalysts. We're using composite inks that you have to make that fit into the production process. Somebody else did this slide. Space age structure. What they mean there is we're using plastics that they use in automotive, these 10, 20-year laminate glues and things. They're really pretty amazing. They stick stuff together, and you can put them in a pressure cooker, you can boil them in acid, you can do all kinds of things, and the stick strength is still quite good. So I'm absolutely amazed at some of the industrial products that are out there to build stuff now. The thing that's important is to get a group of what I call disruptive requirements that, when you do them all together, allow you to do something truly revolutionary. Wow, this slide is way too busy. I guess it's all about the gas sensor revolution, and of course you start, the whole story is this one. This is an interesting story. We started building one at a time of the screen printed sensors. This was a National Science Foundation project, phase 1 SBIR, went to a phase 2, and then we had really good results, so we got a phase 2B. We got a couple $1 million to set up SPEC sensors. The factory, which is mostly owned by other investors, the money guys own everything. But anyways, we do it because it's good science and good engineering. And you have to make a connection to the public if you want to have a large public impact. So at some point, you have to get involved with the business side of things. Anyways, we were doing one at a time, and then we were doing, this is 246 by 424 at a time. And then this is the currently commercial platform. We're building 60 at a time of laminate structures. 60 is the size of an 8-inch wafer, and it dovetails into the semiconductor 8-inch wafer handler that can do automated testing. So there's a method to this madness. You have to consider the downstream manufacturing capabilities and what tools exist, and design, in some ways, not for them, but in an effort to utilize the infrastructure that's there, or have a ton of money. So our vision is to S5. S to the 5 is sensitivity, selectivity, speed of response, stability over time, temperature, pressure, and a $. Those are the 5 S's. And you take the big ones and go to small ones. But what I'm finding now is every time you get engaged with a customer, about 3/4 of them, maybe more, don't want a sensor. They want a measurement. So it's a sensor plus and all sensors are analog, so you need an analog front end, and then you need a digital to give them something digital, because half the world of electrical engineers and instrument designers don't understand analog. They only do digital. And then you need an algorithm on top of that to do, every chemical sensor is temperature, pressure, and concentration dependent, so you have to do chemistry, thermodynamics, and kinetics, so you have to correct for all of these changes in the environment. And I'll show you some examples of that. It's Fox tricorder, of course. Okay, so we have IP. So we're trying to, this is an interesting, and I'll mention this a little bit later, this is more than just a slogan, explosion of innovation. The idea of exponential organizations and exponential technologies is a really interesting one. There's been several books written about it. What it refers to is if you have a capability like a sensor, an analog front end, some computer, so you can make a carbon monoxide measurement in the environment, and it's already corrected in its digital signal, 0 to 1,000 ppm, like home CO alarms or health alarms or whatever. If you can do that measurement and you can provide that platform, like an Arduino, okay, the parallel would be an Arduino electronics or Raspberry Pi. If you can provide that platform to the whole world for a reasonable price, a few bucks, then everybody around the world, all the engineers in the world can innovate. The guy in Chicago can make a parking garage meter. The guy in India can make a cap for policemen who are standing out in the middle of pollution. And everybody, and you see all this innovation. So you don't have to build every product. You just have to build this platform that's enabling, and then the whole world innovates on it. The real issue is, what does it have to do, and what price does it need to be for all this to happen? But if you can get there, you can actually get exponential growth for your organization. The example are some of the shared economy things like Uber and Lyft and these kind of places. So there's a lot of cars driving around, and so it's a share. They call this the shared economy. So you're just using cars that are already driving around. The same is true of the Airbnb. So Airbnb built over 2 million hotel rooms. They had a list of 2 million hotel rooms around the world in 2 years. There's no way a hotel chain could build 2 million rooms in 2 years. You couldn't put it up. You wouldn't have the money. But that's what the shared economy does. You have an empty room in your apartment or your house, and you offer it for rent. And so it goes on Airbnb. It's an amazing paradigm shifts in the way you think about business and the way you think about technology to do the same type of thing, to get large-scale innovation. All right, so my shtick, and this is, I'm giving you the example of me, and I apologize to my colleagues because this is not comprehensive. It doesn't cover many, many, many important topics like curing cancer or detecting cancers and other things that are super important. So I don't want you to think I'm slighting anything, but I'm going to talk about air quality, which is what I focused on, and sensors, and try to give some examples of this. And then, as I've been mentioning, approaches to sensor design, the paradigms that need to change. We'll discuss more about the manufacturing challenges, and I want to get into case studies, which is the only way I know how to do this. So I thought about the question for this meeting, and I said, explaining how to make a fab for sensors to get to a successful factory for nanosensors and a business is difficult on many levels. I mean, this is a book, you know. Simply reporting a series of decisions that I made in an extremely interdisciplinary, multifunctional environment isn't really adequate to do this. Hence the need for a workshop like this, and for people and lots of brains, people smarter than me, to come together and take this information and help to understand it. Know that the boundary conditions for all the decisions we make are unique. Influences are simultaneously financial, temporal, or time-sensitive, market and sales sensitive, and also very technical. And that synthesis is really a difficult job to weigh these, and it takes a team of people. And I have to tell you, I didn't do this on my own. I saw this interesting sensor array, selective layers. All those of you who have been in sensors have seen this in 1980, a long time ago. It's rearing its ugly head, but now it's attached to a drone, which is all right. This is interesting. This is called the Coel bracelet, and it's a project Intel Grameen. Grameen is a not-for-profit in India, Pakistan area, and the Coel bracelet measures CO. They had to make sure it wasn't too ornate, otherwise men would steal it, because they control all the property and wealth in the family. But they made these bracelets and put our CO sensor in it. So we provided 10,000 at cost for this not-for-profit. There's a doctor in Pakistan who is an OBGYN, and he knows that exposure to low-level, even chronic exposure to even low-level CO causes low birth weight babies, and worse if it's high level. And a lot of these homes still have open fires in the rural areas in India and Pakistan. So Intel Grameen have built 10,000 of these, and we built 10,000 sensors at cost. We weren't quite in a position to donate them, but we built them at cost. And they put them in these bracelets, and they're now going to put these out. And during pregnancy, they're going to monitor the exposure to CO. And if it exceeds 20 parts per million, it speaks Pakistani, this little bracelet, and it tells them to get some fresh air. And they're going to see if they can make a difference in the health of the newborns in this area of the world. It's a tremendous experiment, and I suppose I've done too much of this in my life because it distracts me from building my business for my employees. But it's really important, and that's actually the fun part and what keeps me going. So here's one example or one view of manufacturing challenges. Problems in electronics and sensor device industry are rarely associated with chemistry. Most of these are solid-state sensors, and their cameras and their GPS and their accelerometers, proximity switch, all kinds of things. But they're rarely associated. But the amount of chemistry in a product is enormous. I mean, really, the vast majority is upstream, make it out of plastics and glass and all kinds of different materials. And I mentioned both of those because those are only examples of chemicals with tremendous diversity. Success is dependent on the materials choices. And when and where to drive upstream chemistry is critical. How do you start out? If you start out with the wrong plastic and you get to the end and it has to withstand acid environments and your plastic dissolves, your product is dead. So people need chemistry and chemical engineering knowledge throughout the whole process of making a product from invention to the end. However, mechanical engineers actually build products. That's an interesting story. In 2003, I left my full professor position at IIT and I went to the West Coast to work for a Silicon Valley company starting a nanotechnology sensor. And it was the world's first carbon nanotube sensors, right, commercial. Anyway, so they had this company, Nanomix. And I went there as VP of engineering. And I got there, and my task was to build products. And they had about a dozen people at that time. And I asked the CEO, Charlie Janik, who's a really good CEO, I said, Charlie, okay, I'm here. How many, and I was on sabbatical, so I said, how many engineers do we have? And he said, well, we just hired one. And I laughed because scientists don't build products. Engineers build products. You know, I mean, mechanical engineers especially. They build the tooling, they design the tooling, they do all the CAD CAM, and along with tool makers and implementers, but you need mechanical engineers to build products. So I hired 7 mechanical engineers, and we got to a product in a year. But that was a real shock that he said, well, you don't want to hire any scientists? I said, no. If my job is to get to a product, we need engineers. So there's a really, really important synergy between scientists like myself and engineers that has to be not competitive, but very collaborative. And anything you can do to improve that collaboration will help the design and building of products. So we have to proactively approach this. So decisions about unit operation, this is a full-time job, believe me. It takes a lot of effort and a lot of different people to coordinate. And every team is different. You don't hire people with a specification sheet. You think your resume is a spec sheet, but it's really not. It's only a rough outline of what a person is. When you get that person there, then you have to figure out their strengths and their weaknesses. Are they analog? Are they digital? Are they integrators? Or are they work alone kind of people? And so every team is different. And you can't just fire everybody and hire new people all the time. Then you have no continuity. You have to train this team to work together. Kind of like the Warriors, where I live in Oakland, who just won the NBA championship. Congratulations. Congratulations to those guys. They did it last night. That's what kept me up late last night, So if this talk is a little off, it's their fault. So I didn't know where to start with this question that we have for our meeting, except to tell you that there are explorers and farmers, and we need to know when to think like either or both. Explorers are the people that'll go out and try something new. And if you let them go off on their own, they'll often try something that looks really good but crashes in the end, and they fall off the edge of the earth. Farmers are the people that you need in there that come every day to a job and iterate and get things done. You do not want your manufacturing supervisor to be an explorer. He needs to be a farmer. He needs to run what he has there. There's plenty of work to do, and you'll see that in the quality assurance and things. So I just wrote a whole bunch of things that came to my mind about how to get to a supply chain. Now, from our point of view as a CEO or as a NSF, the great relationship I had with NSF through phase 1 through phase 2B, and then even some of the supplementals that we got was absolutely tremendous. NSF was a very good source of support, providing support and reducing risk and paperwork. These are things you can do for an entrepreneur. The other thing is things like you think this debate on healthcare will not have a big impact on companies. When I start a company with 2 or 3 people, I have no bargaining power at all for things like healthcare or insurance for the company. It would be so great to just go to my local post office and say, I want to piggyback on your plan. Just let my guys join your group, or have universal health care, for God's sakes, for everyone, so you don't have to worry about this. But these are actually headaches for a CEO and detract from your ability to actually innovate and get something done. Or you get to hire an administrator or something like that. Anyways, there's a lot of skill sets. Always you're worried about sales. If it's a company, they got to start before you run out of money. The only serious sin you can commit as a company owner, an entrepreneur, is to run out of money. Before you have to have a revenue stream, whether it's a NSF grant, which is a great starter, or it's a venture capitalist or a private investor, but you cannot run out of money, because then you are done. And ultimately, you have to get to customers who can then, in a product that sells over and over again, which is a revenue stream. And that's the CEO's job, is to find the rivers of cash, find the revenue stream that you can get into as quickly as possible. And that's the job, besides being a scientist and an engineer. People ask me, especially when I was in Chicago, about Silicon Valley, because I went out there on sabbatical, and they said, is it an accident? And I don't think so. If you go to California, more than 50% of the CEOs are not native-born Americans. More than 50% have had multiple startups and different things. There's no apology for failure. You look at resumes of people out there. They've worked for 8, 10, 12 companies over the last 15 years. This would not look good on a resume back east. But they reward success. And it doesn't matter where you're from or what you do or how old you are or anything else. If you can succeed and get a business going, then you're rewarded. California has a unique position. It's 25 or 28% indigenous people there. It belong to Mexico, so they're Mexicans. So that's the indigenous population. 40% of San Francisco is Asian. God, I think 60% of Fremont, where we are, is from India. So it's an unbelievable mix of people. My neighborhood, people across the street are from India. The guy that lives next to me is Chinese. There's a few Anglos thrown in between. But I mean, it really is a melting pot like you originally get taught in school that America is. There's not so many of these homogeneous suburbs that you see in the Midwest, where I was in Chicago, where it's all kind of equal status. There's a big company clash between small and big companies. We just had a visit from $1 billion company. They came in and they said, we're going to have our quality engineers come here. We don't even have a quality engineer. I mean, we have quality products. I have a guy who runs the manufacturing plant, but he's not a quality engineer. you have to do this as you go along, and you have to build this as you go along. And it's not until you get a billion-dollar product line like Intel inside, you know, the microprocessor, where you're going to have full-time quality engineers for each factory and things like that. So you have to build all of these skills gradually, and this is an infrastructure that would be really helpful for people like NSF to understand and provide, so that you could hire these guys on an NSF grant or something. I make a distinction between invention and innovation. Invention as a better mousetrap, and innovation as collecting a bunch of ideas and doing something significant that has a social impact. And that's innovation. Complex. So these are the grand challenges from the National Academy of Engineering. And this is my vision of healthcare for all, clean air and water, with clean, sustainable food for everybody, clean energy everywhere. And I have to tell you that I wrote to the MacArthur Foundation their $100 million challenge grant to put sensors, and I would look for other people who want to volunteer for this. I volunteered for this as not-for-profit, but to put sensors everywhere in the world, now that we have low-cost $1 sensors, put them, if you did 1,000 points of monitoring in 1,000 of the most populous centers around the world, you would cover every continent except Antarctica, and you would cover about 65% of the world's population, and you could get a granularity of the tropospheric pollution at our ground level, and this would cost less than $100 million. And it would be a tremendous, like Internet of Things, resource for every college, every university, every environmental health professional, every public health professional, every government. This would be a tremendous resource to have where everyone could learn about what soup they're in and what they're breathing. This is a common problem. Whether you're wealthy or poor, you are breathing the same troposphere, the same air. And I think that would be a worthy thing to do. And I can't imagine doing all these challenges without sensors. Okay, so I'm going to talk to you about why we worry about sensors. And as I mentioned, this is all the air we have around the Earth. And this is what it looks like compared to the size of the Earth. There's not much. And this is all the fresh water that we have. And there's not much. And so we need to start worrying about these things because we're making massive inroads to polluting them and destroying them for ourselves and our kids. And it's leading to public health problems like Flint, Michigan, like Washington, D.C. some years earlier with the lead in the water. Like, you know, and the major threat is mendacity. It's the ostrich. It's putting your head in the sand. It's lying about what's going on. It's having half-truths. It's a misuse of science. Science is there as a guide. So in the early days of understanding the effects of cigarette smoke, sure, it wasn't a proven link beyond 99% statistics between lung cancer and cigarette smoke. But holy hell, if you show these most probable cause and relationship, shouldn't you slow down? Isn't that the prudent use of science? You know, it's not something that proves or disproves fact. It reveals the truth, and it reveals it sometimes gradually. But you have to be aware of what it's saying and what's true and what's not true. Anyways, how are we exposed? Of course, dermal contact causes pollutants to enter our bodies, contaminated food, and of course, inhalation using in the air. The exposome is a concept you ought to familiarize yourself with if you're a sensor person. This Christopher Wild, his concept is just like the genome, all of the innate biochemistry that you have controlled by your DNA and the population of the enzymes and the biochemical systems within you. The exposome is based on the fact that only 3% of the human health burden is due to genetic disease, genetic origins like cystic fibrosis, which is genetic. But 97% is environmental. Something from the outside comes and insults the person. Just think about flu. It's a bug, gets in. Your immune system tries to cope with it, sometimes very well, sometimes not so well. All the air pollutants that get in, all the things you ingest, lead that comes in that centers in your bones. If you become pregnant, instead of calcium coming out of your bones for the fetus, lead comes out along with the calcium. So I mean, all of these things that are in our environment, and if you could understand all of the insults that came upon you from the time you were in the womb and started out until old age, and you know your genome, then you could predict all of the disease burden for that organism. That's the concept. It's parallel to the genome. But it's a very interesting one. It makes good reading. It's happening now. This is a 2015 study that was published in 2015, was 10 years. But they showed 50% of Delhi school children have irreversible lung damage by the time they leave grammar school. Unbelievable. I mean, they're talking about moving all of the schools from Delhi to the suburbs to protect the children. So the story of mankind and our environment, of course, you know, lead, cigarettes, love canal, and now climate change is another big story. This is the 1952 smog inversion in London is credited as the beginning of the environmental movement. And it was so successful when they tracked the smog and SO2 and deaths, and they exactly coincided, and it was so powerful and compelling for the people who were burning high sulfur coal that they actually switched in a matter of just a year or two from high sulfur coal to other forms of energy supply. Unbelievable. And London is now facing a second crisis. If you read the news, I think it was in USA Today yesterday, about London exceeding guidelines, WHO guidelines for air pollution. So what did we focus on as trying to get some traction? And this brings me back to business. These are the ones that right now, CO, NO2, ozone, SO2, particulates, and VOCs are the ones that EPA calls the priority pollutants or the criteria pollutants. And these are the ones that are in our air that we need to monitor. We focused on CO, NO2, ozone, SO2 because those are the ones we could do as a suite of chemicals. So these are just some statistics. And what we need everywhere on the planet is we need actionable information in every neighborhood. You know, there's neighborhoods in Chicago that are just blocks apart. And one neighborhood has a life expectancy of 65 years, another one 85 years. Now, I'm not saying that's due to air pollution, right? But there's something going on in the water, poverty levels, no health care, or something. And this is unacceptable for Americans. We shouldn't put up with this. So here is the important slide on economics. Very little happens on a large scale without economic drivers. Somebody pulls it out. There's a customer. You have to figure out how to monetize this. Otherwise, no one's going to do it on a big scale. So you talk about GDP revolutions. Okay, steam and electricity was the first. The second was the transistor and the computer. And then the US and Japan started to dominate global GDP. The third one is a fusion of computing, communication, and sensing. This is according to the Silicon Valley guys now. It's a consensus there that this is going to lead to $20 billion markets and the third great GDP expansion worldwide. And it's expected to free people from manual labor and leaving them free for creative work. And I told my colleague who wrote this, Janusz Bryzek, I said, not everyone's creative, Janusz. Nor should they be, nor should they even want to be. People should want to be happy and should want to be free to do what they want. Anyways, this was from the Stanford University. There's a group called T-Sensor Summit. It's a trillion sensor universe. And they talk about how do we get into all of these big coming markets that will lead to what's called abundance. Healthcare for all, food for all, clean energy for everybody, water and air clean. So, and there's predictions that say technology is going to move faster than population needs. And so at some point, 2050, we will have enough technology to provide this kind of world. And this is the most optimistic technical prediction I've ever seen in my life. However, since it was done by somebody who understands economics, maybe he's right. And it would be great if he is. And I don't think any political system, if this is true, can stand in the way of technical progress. No one could stop you from buying cell phones and using social media, as you can see. There's no stop to this. Some of these things are really revolutionary and free people. So this is my climate slide. I showed you personal health reasons. This is my climate slide. This is the Larsen B ice shelf in Antarctica. The B shelf already broke off 625 square miles and is supposed to be gone. This is from NASA satellite data by 2020. I expect to be alive then. This is amazing to me that this whole ice shelf is gone. And the sea was just in the news, 20,000 square miles. And it now has an 11-mile wide crack in it, and it will soon be wide enough to actually separate. This is 20,000 square miles of ice, enough to raise sea level some centimeters. So this is truly changing. I mean, NASA's global monitoring system is really showing. So my question is, what do you think if half the state of Florida is underwater? New York has to be moved inland. Extreme weather persists. Droughts worsen. Food prices rise. Forest fires rage. Coral reefs disappear. Species vanish. We have the highest rate of extinction since 65 million years ago, since the dinosaurs, in the present day. Invasive species cause massive deforestation. This is what happens with the heat and the drought. And migration changes. Snow-capped mountains could be a thing of history. This is a very sad and bleak prediction if we don't get our hands around global warming. And the truth will overcome us. It has nothing to do with any kind of belief system. All right, what about gas sensors? This is what I've been doing. Measure everything unambiguously, immediately, no maintenance, tiny and lightweight, and of course, low cost. If you can do all of this in one package, you have yourself a good sensor that might find a market if it's targeted at the right product and the right group of people. So these are the sensors we all know about. The importance of them is they make you aware. They make you feel safe and protected. They make you conscious. And you don't need them all. You remember Helen Keller only had the sense of touch, and she was very aware of her environment. So think about that from a sensory point of view. It's not going to take every sensor of every kind to make giant inroads, but just the right ones at the right time. And they enable us to do action. And this is what your product has to do. It has to enable action by people that's important to them, that they will pay money for. Like, get me out of my house. The fire is raging. So this is my chemical sensor platform. I think I'll just stick to this one. The way I see a chemical sensor is a chemical interface, some way to transduce the signal from that interaction into an electrical signal, and some chemical interface that interacts only with the chemical that you're interested in measuring, and that causes a change. Oh, this is way too busy. I can send this to you if you want. There's a whole bunch of sensors and platforms. I've divided the world over the years into classes of sensor. Chemiresistors are electronic sensors, potentiometric sensors. Those are electrochemical, optical sensors, mechanical and thermal. And they're based on the kind of energy they transduce. And then within that, there's whatever creativity is of the individual. That's another way to organize it. But they're all analog, and they all have to be transduced to an electrical signal so that you get something out that you can work with in an instrumentated sort of way. So the transition, I guess the importance of this slide, we've already talked about a lot of this, but there's really only 3 differentiators you have to work with. You can save somebody money, you can provide them performance they can get nowhere else that's important to them, or you can provide them better service on that product. FedEx is an example of better service than mailing a package. They were able to get packages around. Tremendous model that shows just on the basis of service. A lot of people could carry packages, but just on the basis of service, they built a business. Of course, cost is easy to see. The cheaper cell phone that we all have, and performance. Some of them do the things we need and want, and some of them don't do everything we need. These are the characteristics of a measurement that sensor scientists, I would plead with you for some kind of review of sensor articles that stop calling signals sensitivity. Okay? I mean, I've seen that so many times, and we need to come together on a definition of how to characterize a sensor and what to characterize. So there's three parts of an analytical measurement. Is it precise? Is it accurate? And is it valid? Are there interferences in that environment that would make that measurement not what it is? My CO sensor works really great in the environment, but if you happen to be in an environment with lots of hydrogen, it could be hydrogen and it just looks like CO, it's just electrons. So there are applications that you have to understand to make sure your measurement is valid. And the signal is the signal. That's the difference of the matrix that you're measuring the pollutant in or something like that, minus the matrix without that. And so it's a differential signal. That's signal. And of course, noise can be defined in a statistical way. Sensitivity is the slope of the calibration curve, signal per unit concentration. It's not the signal. Selectivity are relative sensitivities. Speed of response, usually you can't do an exact liftoff and an exact plateau, so we look for something like T90 for T95%. And then stability has to be measured, and that's the stability of all four of these parts or characteristics of the sensor signal with time, with concentration, with matrix, with temperature, with pressure, with RH. And TPRH is important, especially temperature pressure, because this is a thermodynamic and kinetically controlled measurement. And so it's chemistry. And then you have to worry about all of the logistics, cost, size, shape, weight, any application-specific thing. Like we just had this billion-dollar company come to us and say, we're worried about poisoning. Okay, can we leave it out there for 20 years, and how's it going to do? Can you do a 20-year life test? And I said, in the next month? So there are some accelerated life tests you can do, of course. You can go to higher temperatures, increase and accelerate decomposition mechanisms or delamination mechanisms. But unfortunately, there's not a 20-year life test you can do in a year. Okay, case studies. Sensors cross-cut a lot of markets, automotive, health, industrial. You cannot do them all. And market success is vertical, so you got to play in just the ones you want. I like this slide, was done by a Goldman Sachs group for investment, because it shows if you put a sensor in any one of these places, you have a different set of requirements. In the wearables, power is key. You have to find a way to do power. In a connected home or in a connected city or business, often power is not key. I'll go through a lot of these. This is an interesting application. We're involved in the Chicago array of things. Argonne National Lab, the University of Chicago, National Science Foundation, EPA, and a consortium of people, Intel, are building 500 nodes on telephone poles around the city of Chicago, and they contain a whole bunch of sensors. We're doing 7 air quality sensors in that group, and we're hoping that this shows how to do air quality monitoring over urban areas. We're building a little thing called Sparrow. It fits in an OtterBox rail case system. This is going to be available in September, and it'll just slide in, and it'll do everything the home seal alarm does and everything that the Coel bracelet does to protect people. This is our roadmap of taking sensors from phase 1 through integrated parts, through conformal devices, and getting them out to the market. Here's one. We deployed 50,000 of these in London. These are powered by energy scavengers, energy harvester, a Wi-Fi. Anywhere you have 2.4 gigahertz, there's no battery in this device, and it measures the amount of CO. It was just on BBC, and people are carrying this, and they're trying to sell the data to the city. The business model to get people to buy these is they give people incentives, like you get a free cup of coffee at Starbucks if you carry these things and send your data to upload it to the cloud. And then they take the cloud data and they can tell the city where the pollution is at what time of day and what's happening, early warning fire, and they're trying to sell these apps to the city. So it's a very interesting use of technology. This is one we built for NIH just last couple months ago, and it's a wristwatch. We put our sensor in a wristwatch, and we put it on one of our engineers and had him drink beer. We forced him to drink beer. And the amount of ethanol coming through his skin, it lags about 20 minutes before it starts coming out of your pores. But believe me, you can smell it. Anyways, this is him sleeping it off overnight. But anyways, a lot of things are possible. And this could be a game, which is probably a better sale than the serious NIH study that we're involved in, where we said we can monitor alcohol abuse programs and help people, which is the reason we did it. But probably the thing that'll make this commercial is something else. Anyways, I wanted to show you, those are how the gas sensors work, how we build this layer by layer with additive and subtractive processes and screen printing. And I wanted to show you our ozone sensor with our carbon nanotube working electrode. That was the first trial. That's our CO meter over 0 to 100 ppm. We engineered some ionic liquids. This is interesting, molecular engineering, because you can actually molecularly engineer the electrolyte and get particular properties. And when you do that, you can get sensitivity higher than the standard electrolytes for ozone. And this is my token slide for 20 and 5 ppb ozone, which we took out to the field, South Coast Air Quality Management District. And this is carbon monoxide data compared to the red one is the NDIR, which is calibrated daily or monthly, and our device. And this is the statistical correlation, assuming the infrared. The $60,000 instrument is perfect, and ours is not. Now, I tell you, politically, if I had this 0 to 2 ppm measurement, the important part is not that it's perfect, but you can make many measurements with cheap sensors. And the idea is, if this year, this is what my air in South Los Angeles, Orange County looks like, and next year I came to you with a graph where they were all down here, you could, as a politician, stand up and say, I cleaned your air. You could say that. So this $5 sensor compared to a $50,000 instrument is capable of giving you actionable information. We cleaned it up a little bit with temperature compensation and other things, got better statistics. We did ozone with our ionic liquids at different potentials to show how you could differentiate between the two. And I thought there was one more slide here, but I guess not. I guess trial 2 led to this very low-level detection with our carbon nanotube electrode. And I have to tell you, I'm a big fan of nanotechnology now. One thing I wanted to show you was our factory. This is a factory from incoming inspection, assembly, test, singulation, and packaging. Packaging is a big thing that we overlook and don't fund in our research programs. There's a whole process flow. The most important part is it's all dotted with quality control and inspection everywhere. And there's more than that, but those are the official inspection stations for all the different things. This is a typical ramp up to product where you package and you have to do 100% outgoing testing. You have to have yields that are high, so the scrap and waste is low. This takes a while to iterate and get the yield. The supply chain is absolutely critical. We had problems with our plastic manufacturer. We still have problems with our CNT supplier. Unless we grow our own CNTs, which we don't have money to do, we're screwed. We got to depend on other people to make these things. And we bought from Helix, and they went out of business, and now we buy from a US Nano, and they seem to be flighty. Every time we get a batch of nanotubes in, the bulk density is different. They have different hydrophilic, hydrophobic properties. They don't make inks. We got to modify our inks. It's a real pain. So there's lots of problems to solve and to work on. So this is our capacity chart. We can do about 2 million a year now out of our facility. This is what our sensor package looks like from the raw sensor. Put it on a board, put it in an encapsulant, depending on what the customer wants. The paradigm has to shift for us from looking at sensors. If you're doing R&D, you need to look at sensors, and you need to look at all the characteristics of sensors and get better sensors by technology. But if you're looking at making a product, you have to look at it by architecture and process, and you have to result in a package that you can somehow set up manufacturing and make. If I had $100 million, I could do a fab from the ground up. Would that I could do that. Anyways, sensors are going toward systems and display. And this is Robbie the Robot, 1955, Forbidden Planet. Leslie Nielsen, one of his first films. And he was my hero. He was the guy that got me interested in science. I was only 9 years old. So this is where we're going with all this. We usually get a roller coaster ride, and sometimes we wind up with the big catch. So this is my pitch to you, that we save our planet with technology, whether you're doing sensors for cancer, or sensors for environment, sensors for water, or any kind of sensors. Be very vigilant in your work, and good luck with all of your science and engineering. Thank you.